All right, continuing our discussion on equilibrium. You can see we're going to do 710. This is, as you can see, 54 slides is pretty intense. So we're going to break it into two parts. So again, encouraged to start the homework so that you don't have too much in one shot there. So what we're going to do right now is relate this equilibrium to solubility. So just a couple of, hopefully, reviews for you about a solution that if it is saturated, that means you've added as much solute as possible to the solvent. All right? And really the only way to tell this, and I would highlight or underline this, is there will be some solid solute will remain on the bottom of the container. Say you're mixing a beaker. So you stir and stir and stir and stir and stir, and no matter what, some solid settles down. Usually you're making a saturated solution, you would err on the side of having lots of solid at the bottom. And that's how you're guaranteed that a solution is at equilibrium when it reaches that point. All right, so this is a kind of a nifty little graphic of that. There's your solid that's settled at the bottom. AB solid going into its constituent ions. That's the reaction. That's the chemical reaction that we're going to be looking for. And again, the rates will be the same going back and forth. There'll be just as many aqueous ions forming solid as there are solid crystalline solids breaking up into their ions. So it's a equilibrium system. All right, so how do we approach this with equilibrium constant? Well, we talked about how KEQ has several different groups, KC, KP, the parentheses, and now we have KSP. And as you can tell from the title here, the KSP stands for solubility product. And the reason that they give this a special name is if you're talking about a solid dissolving in an aqueous medium, you're always going to have a solid on the left side, meaning that there'll never be anything on the bottom of your equilibrium expression. So this breaks into its two ions, one monatomic, one polyatomic, and that's two things. So I think some people get a little confused by that and think that it's more complicated than that, but there's a calcium ion and a carbonate ion that it breaks into. So your reaction then becomes the product of those two things. So that's why it's a solubility product. Now, obviously, you'll have instances where this is really three ions, if you look at it. One positive 2 lead ion and 2 chloride ions. So to write the solubility product, you would, again, it's just you're multiplying the two ions together, but you do have a coefficient involved in this, and sometimes both of them will have a coefficient. Now, the KSP, the problems that we're doing, usually in the 1 times 10 to the minus 3, 1 times 10 to the minus 54, super insoluble. And again, tiny little I when we said things are insoluble. They are soluble to a certain degree, just not very much at all. So you will run into examples like this. Now, you have solubility rules on the back of your yellow sheet, and you're still welcome to utilize those in doing these problems. But I think if you could remember that the ones that are always soluble: sodium, potassium, ammonium, and then nitrate for the anion. That'll be really, really helpful. And when that happens, when you see such a high degree of solubility, then the KSP is going to sneak above 1. And that's because you're getting all products, big number on the top, small number on the bottom. So the equilibrium systems are hard problems to do with a soluble salt because we need to achieve that equilibrium. We could talk about Q state for this, but until this gets saturated, and even a completely soluble, there are limits. You'd have to dump a lot of salt in water for it to not dissolve anymore, but this, you could reach an equilibrium with this as well, as these double arrows show here. All right, so if you're given a question like this, so you have calcium carbonate versus lead chloride. They both have relatively small numbers, and a lot of times you'll see the temperature expressed because the degree of solubility can change with temperature. So you got these two nice little equilibrium systems here. And the question is, which one is least soluble? And of course, 298 Kelvin is the same as what they wrote in Celsius down here, because you're, remember, adding 273. So we're looking at this going, okay, which one would be the least soluble? All right. Well, you want to get this kind of hammered in there, that these tiny values, the ones that are the smallest, are going to mean that they're the least soluble. And that should make sense, because we said if they're greater than 1, then they're soluble. So there's a degree of solubility between these things. It would be a little bit easier to get lead chloride dissolved. As a matter of fact, when we make these solutions, we just add a little tish of acid in there, and that helps dissolve them. I think we're going to talk about the chemistry of that. I can't remember if that's still in the curriculum or not. But so calcium is just something that's not very soluble. And if you think about it, it's kind of like chalk. And for those of you that remember chalk, well, of course you have your sidewalk chalk now, don't you? Those are not going to, dissolve in water very well. All right, so here we have a system right here of the lead chloride going into its ions. Now, to figure out when the solubility is the maximum molar concentration for a given temperature, we look at it as a molar ratio between these things. And we're going to need this when we're doing our problems. So for every 1 mole of this, you have 2 moles of that. So the solubility portion of it is equal to the concentration of the lead, or half of the concentration of the chloride you could use to figure out what the solubility of that is. And that's when it is saturated. So this is a little easier to understand with the problem here. So we're going to go ahead and do this. Really important that you try A, to make sure that you can take lead fluoride and write that KSP expression. So on that next blank slide, do that one on your own. Hit the pause and get it right with the symbols, with the S and AQ symbols. All right, so hopefully, since the similarity with this was with the example, that you're able to jump in and do this. Okay. Now going back, B says write the equilibrium expression. So it's a something dissolving. So you would say KSP equals the concentration of the lead ions plus the fluoride ions squared. All right, now for C, they asked us to find the maximum molar concentrations of those ions. So this is where it gets a little bit tricky, but I think once you see one of these, it'll make a lot of sense to you. So what you're going to do is the KSP was given in the problem, and then you're just going to use lowercase s as the molar solubility. Certainly you could use an X in this problem, but this is just common practice, and it's a really good idea to do that on the AP exam, to use an S for molar solubility. So you take S. Now notice what we did here. We doubled the S and we squared it because this is a 1 to 2 molar ratio. We do that because of the concentrations, and we do the 2 because of our rule for writing equilibrium law expressions. Therefore, you get to do a fun little cubed root problem where you solve for S, and of course you can, caret key raise that to the 1/3 power, and if you cannot easily find your cubed root, but I think most of those calculators, you use those math functions, that cubed root key will be on there. So this is really, really common in the KSP, is to have to solve for a cubed root. And when you do that, and hopefully when you crunch those numbers, you get 2.1 times 10 to the minus third molar. Okay, and remember that your calculator will say 0.0021. If it's off by a tenth or so, don't get too bent out of shape. I'm not positive that that's the right answer, but obviously it's going to be real close to that. So that's how we figure out what the lead is, and then if you want to figure out the fluoride, all you got to do is double that number. And the math is actually pretty easy. This would be one that might be on a multiple choice test. You're like, oh no, I got to take that times 2. Well, it's the same power, so just 2.1, double that up, 4.2 times 10 to the minus third molar. All right, and that's doing the solubility product constant. All right, so we've got a really important summary of what we're talking about here. We're going to be looking at Q, and we're going to be looking at the K values. So this is nothing brand new. If Q is equal to K, the system's at equilibrium, and it's a saturated solution. Now, if the QSP is greater than the KSP, then you know a precipitate will form. Okay? So if you could solve for the QSP and be given that KSP value, then you'll say, well, the reaction's going to proceed to the left until it reaches equilibrium, and it just means it has all those excess ions, so a precipitate is going to be there until it reaches equilibrium. So, and if you have a really small Q value, then no precipitate will form. In other words, if it's less than KSP. So we're going to do a problem coming up with that, and that's this one. But we'll do that on the next slide because this problem is fairly involved. So we just got 2 lectures, and then you can get started on 2 lectures today, and I don't know how many on the next class, but you definitely will be able to get started on those problems. Okay, so end of lecture 1.